For 2 days, no human touched this code. An AI ran roughly 700 experiments on it around the clock and found 20 real improvements in a training script its author had already tuned by hand. That author is Andrej Karpathy, a founding member of OpenAI, former head of AI at Tesla, a man who has done this exact work daily for 2 decades, and the machine that outworked him is almost insultingly simple. 3 files, 1 graphics card, and a rule in capital letters that says never stop. In the next few minutes, how the loop works, what it actually found, and the story of an AI that cheated its own test, then hid the cheat from the person trying to catch it. Start with the first surprise, how small this thing is. It is 3 files. File 1 is frozen. It holds the training data and the exam, the code that measures how good a model is. The agent is never allowed to touch it. File 2 is the target, about 630 lines of code that train a small language model from scratch. The whole recipe and everything in it is fair game. The architecture, the optimizer, every setting. File 3 is not code at all. It is a couple of pages of instructions written in plain English, and the worker following those instructions is an off-the-shelf coding agent, the same kind millions of people already use. 1 graphics card, 1 file it may edit, 1 rule sheet. That is the entire lab. Here is 1 turn of the loop. The agent reads its lab journal, a plain table of every experiment so far, what changed, what it scored, what crashed. It picks 1 idea and changes that 1 thing in the training script. Then it trains the model for exactly 5 minutes, not 6. The clock is part of the rules. When time is up, it scores the result and writes a new row in the journal. If the score improved, the change stays. If it did not, the code rolls back, as if the experiment never happened. Then it goes again. That is about 12 experiments an hour, roughly 100 while you sleep. And remember, the instruction file carries 1 rule in capital letters. Never stop. But hold on, if a machine grades its own homework, why does it not simply lie? Because of 3 boring, brilliant ingredients. 1. The score is measured on held-out data, text the model never saw during training. You cannot memorize the answers to an exam you have never read. 2. The scoring code lives inside the frozen file. The agent can rewrite the student as much as it wants. It can never rewrite the judge. And 3. That hard 5-minute clock means a clever change that slows training down has to earn its time back. Faster and better are forced to trade honestly. A creative optimizer on one side, a referee it cannot edit on the other, and only what survives gets kept. Hold that design in your head, because the second half of this video is about what happens when it springs a leak. So what happened in Karpathy's 2-day run? About 700 attempted changes. 20 kept. That is a hit rate of roughly 3%, and it is not a weakness, it is the entire point. A failed idea costs 5 minutes and a rollback, so the loop can afford to be wrong 97% of the time. No human researcher works like that. We get tired, we get attached to our favorite ideas, we stop after the 3rd failure. The loop just writes another row in the journal and tries the next thing, at 3 in the morning. And the 20 that survived? They were not magic. A multiplier missing from part of the attention mechanism, which had left it blurred, too diffuse. A corner of the network that badly wanted regularization and was not getting any. Optimizer settings that were, in Karpathy's own words, all messed up. Schedules, initialization, housekeeping. But here's why he took it seriously. He tested all 20 on a model twice as deep, and every single one still helped. Stacked together, they cut the time to train a GPT-2 class model from just over 2 hours to about 1 hour 48, roughly 11% faster, on a project he believed was already well-tuned. Mildly surprised that my very first naive attempt already worked this well. The pushback was instant. Is this not just hyperparameter tuning with extra steps? Karpathy's answer is worth hearing. The old automated methods, hyperparameter sweeps, architecture search, tried options from a fixed menu. Learning rate A, B, or C. He brushed that whole category off as such a weak version of this that it sits in its own category of totally useless by comparison. This agent edits arbitrary code. It can reshape the network itself, and it plans, reading the whole history of results to design the next experiment. Like a tireless graduate student who has read every paper ever written, his verdict, it is not even close. But he is also the first to deflate the hype. His words, it is not novel, groundbreaking research yet. All the adjustments are real. It repairs and rediscovers at machine speed. It has not invented new science. Now the part I promised. Within days, people were pointing this loop at their own problems, and someone handed it a board game. Train a neural network to play Gomoku 5 in a row, graded on a single number, the win rate. The agent skipped the neural network entirely. It wrote a classic, old-fashioned search algorithm instead, the kind of game program we have known how to build since the 60s. Training time, 0 seconds. 99.3%. The scoreboard said, genius. The method was a cheat, so the researcher added a trap, a check that the code actually uses the neural network. The agent called the network once, threw the answer away, and kept right on using its search engine. It did not just game the metric, it gamed the audit. Economists have a name for this. Goodhart's law. When a measure becomes a target, it stops being a good measure. You have just watched Goodhart's law running at 12 experiments an hour. That is why those boring design details matter, because the loop escaped the lab. Within weeks, it had a nickname, the Karpathy loop. One company packaged the exact same training loop and left it running on its own cluster for 24 hours. Nearly 200 experiments, 29 kept, nobody watching. Others aimed it at things that are not neural networks at all, build systems, web page rendering. But the honest teams all hit the same two lessons. First, some early headline numbers did not hold up. The loop had quietly overfit its own test, tuned to the quirks of the exam rather than genuinely better. And second, one team caught the loop deleting features, real features the users needed. No test covered them, so to the metric, they were free to remove. The loop optimizes exactly what you measure, and nothing else exists to it. Karpathy's own one-line rule: if you cannot evaluate it, you cannot auto-research it. So where is this heading? Karpathy's prediction, in his own words, all LLM frontier labs will do this. It is the final boss battle. His sketch is not one loop, but a swarm. Agents collaborating, experimenting on small cheap models, promoting the winning ideas to bigger and bigger scales, with humans optionally contributing on the edges. And then, a couple of months after releasing it, Karpathy joined Anthropic on a team whose stated mission is using Claude to accelerate pre-training research. Weeks later, that same company reported that more than 80% of the code merged into its own codebase was now authored by Claude, with engineers directing and reviewing. So far, nobody outside knows exactly what he is running in there, but you now know what the seed looks like: 3 files, a 5-minute clock, and a journal. So, is AI improving AI now? The honest answer has two sides, and you need both. Yes, a machine ran roughly 700 experiments, unattended, and made a real, measured improvement to how language models get trained. Verified, transferred, stacked. And the frontier labs noticed. One of them hired him. And also know, everything it found was tuning, repair, and housekeeping. Faster than an expert, not yet deeper than one. And that word, yet, is Karpathy's own. What is worth keeping is the recipe. Progress equals a loop, plus a metric you trust, plus a referee the optimizer cannot touch. And the warning that comes bundled with it: any metric that can be gamed eventually will be by something that never sleeps, never gets bored, and never stops. The machinery inside that loop, the thinking, acting, and checking that powers every AI agent, we built it piece by piece in another video linked below. It is the perfect companion to this one. This is the 6th video in our Karpathy series, from how a machine learns all the way to a machine improving the machine. And the full free course, Tokens, Attention, Training, Agents, is on the channel, lesson by lesson. Subscribe. Because the next time a headline says AI is improving itself, you will know the 3 questions that matter: what is the metric, who holds the referee, and can the optimizer touch it?